Hey, what's up, you guys? So in our previous videos, we covered questions 1 through 4. Now, in this video, we'll proceed with question 5. So this one right here. Now, before diving into the solution, let's begin with our routine practice of revisiting the steps to approach the problem. Now, like I mentioned earlier in my previous videos, that the reason we do that is so that we stay focused and we follow a clear path and, hopefully get the answer with confidence, right? Hopefully you want to get the correct answer and we want to be very confident about our answer, right? So let's now talk about the steps. So our first step was that we substitute our power series representation, that is our y prime, and our y double prime into our differential equation. And then we have our second step, which was we need to match our powers of x to an n such that it looks like this, x to the power n. And then we'll try to shift our indices, right? Like the starting index of all the series so that they start from the same index. And like I mentioned in our previous videos, if we have multiple series of multiple indexes, we will try to keep the one that's the largest, that's the biggest index, and we'll try to shift the series with smaller indexes so that it also starts from the larger index. And then our fourth step would be combining all the power series to just one. And then we'll solve our coefficients, right? Using our recurrence relation. That is what this section is all about. And then finally get our solution, which obviously would be in this form right here. Okay. So these are the steps. So let's get right into a problem then. So this is my problem 5, and I'm just going to copy my question. So I have y double prime minus x times y prime plus y equals 3. So at our right-hand side, it's a 3. So it's not a 0. That means this is a non-homogeneous equation. Okay, so now our first step was to substitute our power series into our differential equations. So let's do that. So by now, we should all know that our y is equal to summation from n equal to 0 to infinity, a sub n x to the power n. Then I have my y prime, and since I'm deriving it, my starting index is 1 to infinity, a sub n times x to the power n minus 1. And then since I'm deriving it once again, hence my starting index increases by 1 again. So now it's going to start from 2 to infinity, a sub n times n minus 1 times x to the power n minus 2. Okay, so I have these 3 power series expressions. So I'm going to use different boxes like I do to add some colors. So I have my red box for my y, my green box for my y prime, and my blue box for my y double prime. So now let's substitute that in my equation. So first I have my y double prime. So I'm going to write that in my blue. So I have summation n equal to 2 infinity, a sub n times n minus 1 times x to the power n minus 2. Then I have my x, and then I have my y prime. So now the green letters, so from 1 to infinity, a sub n times x to the power n minus 1. And then I have my plus y function, which is in red, to infinity, then a sub n x to the power n equals 3. Let's not forget the 3. Okay, so now we can see that we have our extra x, so why not just multiply that, distribute that with my second power series. So I'm going to rewrite that again. To infinity a sub n times n minus 1 x to the power n minus 2. Then I have my minus. So I have n equal to 1 to infinity a sub n times x to the power n. And again, the reason why, it's because of the rules of exponents, which says that if my bases are the same, then my exponents adds up, right? So I can see that my base is an x, and their exponents is 1 and n minus 1. So I'm going to add that up, and when I do that, I have just an n. And then my plus summation n equal to 0 to infinity a sub n x to the power n equals 3. All right, so this is what it looks like after we've successfully done our first step, okay, which was basically substituting our power series into our differential equation. Okay, good. All right, so now we move on to our second step, which was basically making sure that these exponents right here, the powers of these x's, are n. And I can already see that the power of my second one and my third power series, they're already in n. So we don't have to do anything with that. But the power of my first power series is n minus 2. So this is the only one that we need to work on so that it also becomes n. Okay, so my second step would be to match the exponent or power of x of my first power series to an n. All right, so I have my first power series that starts from 0 to infinity a sub n times n minus 1 x to the power n minus 2. And I know that it needs to get transformed to just an n. Okay, you know what? I'm thinking of using a different color, like a more darker blue. No particular reason. It just looks nicer. Okay, so I feel like it's gonna look nicer. All right, so I'm going to just use this blue. Okay. All right. So now I know that my n minus 2 has to be an n. And if you observe clearly, all we need to do is just add 2 in it. And then I can see that my negative 2 cancels out the positive 2. So I'm left with just an n. So all I need to do is just add a 2. Okay. So since I added a 2 on my n, that means I also need to add my 2's in all of my n's in these power series, okay? So that means my a sub n gets transformed into a sub n plus 2. Then my n over here gets transformed to n plus 2. And then my n minus 1 over here also gets transformed. So now I have a plus 2. So now when I substitute that over here, I get n plus 1. Okay, so I can see that by transforming this, I have my power to an n. Now, since I increased all my n's by 2, that means that my starting index decreases by 2. So that means it's going to start from 0 instead, to infinity instead of 2, since all my n's increases by 2. Okay, so this is how my first power series, my first transformed, oh my God, like just saying it out. Okay, my first power series look like after it has been transformed. Okay, so now let's rewrite that. Okay, let's just write our new transformed power series. So now it has become summation from n equal to 0 to infinity a sub n plus 2 times n plus 2 times n plus 1 times x to the power n. And then I have my minus, just rewriting the rest of my power series. Okay, so I have summation n equal to 1 to infinity a sub n times x to the power n, then plus, then again, summation n equal to 0 to infinity a sub n x to the power n equals 3. Okay, so we have successfully worked on our second step, which was making sure that the exponents or the powers of x, these ones right here, are all n. And we can see that they are indeed. Okay, so now my third step was to make sure that all of these power series start from the same number. That means they all have the same starting index. Now, which one do I keep, right? So like I mentioned earlier, that we always leave the series with the largest starting index. So this one right here, as I can see that this is the only one that starts from 1. And the first one and the third one, they start from a 0. So clearly this one's the largest one, the second one. So that means we have to shift our first and third power series, since they are like the smaller ones. Okay, so now that means we have to write our smaller terms, that is n equal to 0 term, for both my first and my third power series separately. Okay, so let's go ahead and write the terms for n equal to 0 for both of the power series. So I have my first power series, which is from n equal to 0 to infinity a sub n plus 2 times n plus 2 times n plus 1 times x to the power n. So now when my n is equal to 0, so when n equal to 0, that means our power series becomes a sub 0 plus 2 times 0 plus 2 times 0 plus 1 times x to the power 0, which gets simplified to 2a sub 2. Okay, and then I have my third power series, which is summation n equal to 0 to infinity a sub n x to the power n. And then when n equal to 0 for this one, I have a sub 0 x to the power 0, which gets simplified to just a sub 0. Okay, so now let's write these terms separately. So I have 2a sub 2 plus, and then my first power series, so taking out my blue ink. So now it starts from 1. Okay, n plus 2 times n plus 2 times n plus 1 times x to the power n. And then I have my second power series, which is n equal to 1 to infinity a sub n times n x to the power n. Then I have the first term, like n equal to 0 term for my third power series, which was a sub 0. And then running out my little space over here, that's fine, I guess. That just equals 3. Okay. So I can see that I have successfully performed well on my second and my third step, which was making sure that the powers of x is the same, that is n, and my starting index is also the same. Oh, I should have written over here as 1. Sorry about that. Okay. So now it also starts from 1. All right. So that means I can finally combine them into 1, right? So that is our fourth step. So let's go ahead and do that. So I have my 2a sub 2 plus the a sub 0 from here. And now combining all of them together. So now it's going to start from equal to 1 to infinity. And as I can see that all of them has the x to the power n as common. And then just writing the leftover terms for each of the power series. N plus a sub n equals 3. Okay, now I have space for my 3 over here. Okay, so I can see that it looks pretty good so far. Okay, so now our next step, which was our fifth step, was to solve our coefficients. All right, so to do that, like we have done previously, we will look at what we have got on our right hand side and what we've got on our left hand side. So now we'll look at these two terms, right? And I can see that they are constants, right? They do not have any x attached to it, right? And if I look at my right, I can see that the only value I'm given is also a constant, right? That it doesn't have any x attached to it. So I can put them up together. I have 3, okay? And we've already discussed in our previous videos that our a sub 0 is always an arbitrary number, right? And since it's second order non-homogeneous differential equation, I can tell that my a sub 1 is also an arbitrary number, right? Because I'll have 2 arbitrary numbers since my differential equation is second order, okay? Even though my a sub 1 is not given over here, it's not over here, but I know at the back of my head that this is also going to be an arbitrary number. Okay, so I can now find my a sub 2, all right? So I have my a sub 2 over here, isolating them, divide by 2. Okay, so this is my a sub 2 over here. Okay, now I'm going to look for the rest of my terms, the rest of my coefficients for x, right? So if I look over here, right, this power series, they start from n is equal to 1, and then n equal to 2, then n equal to 3, n equal to 4, all the way up to infinity. And I can tell just by looking at what I've got on my right that if there is an x attached to my value, then it's going to be a 0, right? Because I can see in my right that there's no coefficients, right? There's no x's, right? So that means this entire thing becomes a 0 just when there is an x attached to it, okay? So that means plus 2 times n plus 2 times n plus 1 minus a sub n times n plus a sub n equal to 0 when my n is greater than or equal to 1. Okay? All right, so let's now isolate our a sub n plus 2. So I have a sub n times n minus a sub n divided by n plus 2 times n plus 1. Okay, and this is our recurrence relation. Okay. Now in this question, I have to generate some terms using my recurrence relations, right? So I can find my coefficients. So let's go ahead and do that. So now I said that this is valid when n is greater than or equal to 1. So let's go ahead and find some terms, okay? So I can say that when n is equal to 1, then I have a sub 1 plus 2, which is a sub 3, which is a sub 1 times 1, which is just 1. And then I have minus a sub 1 divide by 1 plus 2 times 1 plus 1. And I can see that in my numerator, it's a 0. Okay, so I can tell that my a sub 3 is basically a 0. Okay, all right. Then let's go ahead and find my n equal to 2. So I have a sub 2 plus 2, which is a sub 4. That is equals 2a sub 2 minus a sub 2 divide by 2 plus 2 times 2 plus 1. And gets simplified to 1 by 12 a sub 2. And I have my a sub 2 over here, which is 3 minus a sub 0 by 2. So let's just plug in that value over here. So I have 3a sub 0 by 2. Okay. We can just leave this as it is, or if you just want to further simplify, you can do that too. So let's just further simplify that. Okay. All right. Now, another thing I want you guys to observe that this 24 can also be rewritten as 1 by 4 factorial times 3a sub 0, right? Now, I don't know why I have this factorial right now, but the thing I like to do is just to see the possibilities, right? And the reason why this kind of came up because I looked initially that for my a sub 2, I have divide by 2, and I know that 2 can also be written as 2 factorial, right? And then when I got the result for 24, I noticed that, wait, 24 can also be written as 4 factorial. So now I'm thinking maybe there can be some factorials involved in this situation, right? Again, I'm not sure. To be sure, I have to write more terms, but this could be a possibility, right? So this is the only reason why I thought maybe writing 4 factorial could be like, a hint of something. Okay, so I'm just going to draw a box in that too. Okay, all right. Now let's go ahead and work for n is equal to 3. So I have n equal to 3, then I get a sub 3 plus 2, which is a sub 5, which is 3a sub 3 minus a sub 3 divided by 3 plus 2 by 3 plus 1. Now, when I further simplify it, I get 2 by 20 a sub 3. Now, if you look in over here, I can see that my a sub 3 is equal to 0. So that means this is 0. Hence, my a sub 3 is a 0. Okay. Oh, it's supposed to be a sub 5. Excuse me. Okay. The reason why I draw these boxes around each of the values so that, it helps me find it when I have to add them in my general solution. When I have to take them, you have to bring them in my general solution, right? So since there's a lot of numbers over here and there, so it kind of gives me it helps me out to figure out and it's just highlighted so I don't have to look for those values. Okay, all right. Then I have n equal to 4. Which is a sub 4 plus 2, that is a sub 6, equals 4a sub 4 minus a sub 4, divide by 4 plus 2 times 4 plus 1, which is 330 a sub 4. Now I can see that my a sub 4 is 1 divided by 24 times 3 minus a sub 0. So let's just plug in that value over here. So I have 330 times 1 by 24 times 3a sub 0. And then if you multiply 30 by 24, I get a 720. Then 3 minus a sub 0. Now, again, coincidentally, if you observe that 720 can also be written as 3 by 6 factorial times 3a sub 0. Okay, so now since my third, there's like another third hint that there's a factorial, so I can tell for sure that there's definitely some factorials involved in this series, okay? So now I'll try to write all of the terms in factorials now, okay? So let me draw the box. Oops, okay. Alrighty, so now let's move on to n equal to 5. So equals to 5. I have a sub 5 plus 2, which is a sub 7. And that is 5a sub 5 minus a sub 5 divided by 5 plus 2 times 5 plus 1. And if I simplify that, I have 4 by 42, a sub 5. And I know that my a sub 5 is a 0. That means it's a 0. Hence, my a sub 7 is a 0. Okay. Then let's move to n equal to 6, which is a sub 6 plus 2, which is a sub 8. That is 6, a sub 6 minus a sub 6 by 6 plus 2 times 6 plus 1, which gives me 5 by 56, a sub 6. And I can see that my a sub 6 is basically 5 times 56 times 3 by 720 times 3 minus a sub 0. And again, if I try to further simplify the denominator, I get 40320. And then I'm just going to keep my 3 times 5 as it is, just to see some sort of a possibility. And I can see that this value is basically 8 factorial. Factorial, 3a sub 0. So now that is my a sub 8. Okay. And then I have my n equals to 0, n equals 7, my bad. That is a sub 7 plus 2, which is sub 9, equals 7a sub 7 minus a sub 7 divided by 7 plus 2 times 7 plus 1. And I know that this is a 0 because my a7 is a 0. Okay, so that means my a sub 9 is a 0. And then for now, let's just keep our n equal to 8 as our last term. So 2 a sub 10 divided by equals 8a sub 8 minus a sub 8 divided by 8 plus 2 times 8 plus 1. That is 7 by 90, a8, and my 8 is right over here. So I can write 3 times 5 times 7. And then I have my 90 times 4, 0, 3, 20. And then my 3 minus a sub 0. Now, if you further see that, you will realize that this value right here is nothing but 10 factorial. Okay. 0. That is my A10. Okay. So I think we are now ready to write our general solution. So let's go ahead and do that. So I have yx equals a sub 0, which is, again, my arbitrary number. And then I have a sub 1, which is also an arbitrary number. And then I have my a sub 2. So if I look for here, my a sub 2 is 3 minus a sub 0 divided by 2. So I'm just going to separate 1 by 2, and since I have factorials, so I'm going to add the factorials over here. Then I have 3 minus a sub 0. Can forget my x squared. Then I have my a sub 3, and I've seen that my a sub 3 is basically 0. So I'm going to now move to my a sub 4, and I can see that my a sub 4, so over here it's 1 divided by 4 factorial. So I'm going to write that. So I have 1 divided by 4 factorial, 3a sub 0, x to the power 4. And then I've also found that my a sub 5, so basically every alternate odd numbers, they are 0. And then I have my a sub 6, which is 3 by 6 factorial. I'm going to write that. So I have 3 by 6 factorial, 3a sub 0, x to the power 6. And then I have my a sub 8, which is 3 times, my a7 is 0, so we'll skip that. Then I have my a sub 8, which is 3 times 5 by 8 factorial. I have 3 times 5, 8 factorial, 3a sub 0, x to the power 8. Again, I have my a sub 9, which is a 0, so I'm going to skip that. And then I have my a sub 10, which is 3 times 5 times 7 divided by 10 factorial, 3 minus a sub 0, x to the power 10. Okay, and then so on. All right, so now this is what my solution looks like. Now, like I mentioned earlier, you can leave this answer as it is, right? But if you're like me, if you're like, oh, I want to, simplify it further, just take out my 3 minus a sub 0, because you can see that it's quite common after my second term, right? This is my first term, this is my second term. So after my second term, I can see that there's 3 a sub 0s everywhere. So clearly I can see that I can take that as common. So just further simplifying it. Again, this is not mandatory for you guys to do it, but if you want to do it, you're more than welcome to do that. So I'm going to just take the 3 minus a sub 0 as common. Then I have by 2 factorial x squared plus 1 by 4 factorial x4 plus 3 divided by 6 factorial x6 plus 3 times 5 divided by 8 factorial x8 plus 3 times 5 times 7 divided by 10 factorial x10, and then so on. Okay, so this is my more simplified form of the solution. Okay, so again, like I said, this is not mandatory for you guys to do it. You can leave the answer as this one right here, but if you want to further simplify it, again, you can do it. So I thought I should give you like both options. Okay, all right, so I hope that you enjoyed watching this video as much as I enjoyed making it, and I will see you in my next video. Bye bye.